Welcome, everyone, to episode 8 of the Manufacturers Podcast. This week, we're going to be discussing topology optimization. This is somewhat of an advanced manufacturing topic, but I feel it's beneficial for anyone from a high school student all the way up to an experienced engineer. This is a relatively new technology or resource in the scheme of things, and it's the best way to keep relevant is to always be looking and researching. And this is a great topic to discuss, and it can really elevate your design game to the next level. So let's get to it. Welcome to the Manufacturers Podcast, the only source to bring you raw, unfiltered experience from those in the manufacturing and skilled trades world. If you are looking to learn and develop your skills, you found the right place. Strap in and stand by. Welcome, everyone, to week 8. As I said, we're going to discuss topology optimization. So what that means, you may not be familiar with that term. Topology optimization and also generative design, they're more of a design resource than a CAD tool. They work and function very similar to CAD, but they're kind of a secondary process. What we're going to be going over today is topology optimization, and there is a little bit of difference between the two. When you think generative design, which is a term you hear floated around a little more than top op, there are some key differences. So essentially, topology optimization is a tool to take a geometric shape or a part, even a part or what represents what would be a part. You apply a certain load and a constraint and target values, and what it will do is subtract material to try to come up with the lightest weight part, the least amount of mass, and retain a certain structural compliance, basically a strength. And it can also factor in other engineering factors such as a thermal load or pressure and whatnot. And generative design is a little more like, instead of being a subtractive type of approach, it can be a growth. And it also revolves around your manufacturing process and your material. So with topology optimization, if I have this remote control and I want to make that out of a material, it could be isotropic, anisotropic, amorphous, whatever. I can model this remote control just as it is, or I can model the outside dimension. And if I want to keep these buttons, but I don't care about the rest of the material, the rest of the shape, I can define these buttons as a boundary. I can apply certain constraints, such as force. I need it to withstand a certain amount of grip, or to drop it, so it has to have a certain amount of impact resistance. And the software will then, through multiple iterations, it will generate the best possible outcome for that. In this mic here. With generative design, it's going to work a little differently. It's going to also account in for our manufacturing process, whether that's CNC machining, 3D printing, and from there it can even break it down to different printing processes, such as powder bed with a metal AM process, or filament deposition, or some programs now can even run like resin and SLS, like sintering. So it's kind of more of a manufacturing, add on. Generative design accounts for a lot of things, and you can also put in targets such as you want to retain a certain amount of strength while using the least amount of material. So, from a manufacturing standpoint, that's advantageous. If you want to save cost or time, how fast can I build something? How the amount of material? I mean, material costs money, so the least amount of material we can put in, the cheaper the part is going to be to make. Where topology optimization is more of a pure engineering tool. And what it does very well. Now, we're going to be discussing mainly topology optimization, and there is a little confusion. Some people refer to generative design as topology optimization, which the function, or essentially the method in which it's, creating its final shape, is like topology optimization. It's just counting in a few different factors, with generative design. But we're going to be focusing on top op. I think it's a little more applicable. You can do this in SolidWorks as well as Fusion and Siemens NX and Creo. So, a topology study in SolidWorks, that's something more people are going to have access to. It's going to be a little more applicable. And, we're set up for that here. So, if you have software like Fusion 360, I know we talk about that quite a bit, and it's a great software. To have the generative design package, you have to be a subscriber. So you're going to pay. Right now, I think there's different price options depending. If you pay for the full year, it's cheaper than by paying by the month, and I think it's $495 right now for a Fusion 360 subscriber package for 1 year. Otherwise, it's $60 a month. And if you pay for 3 years in advance, I think it's only like $1,400 or something, or $1,300. But we're going to be using a software called Topology. It's one, I have a license for, and I really like how it works. And it works on a different basis than Fusion 360 or even SolidWorks. And we're going to be able to go through a lot more in a shorter amount of time. And it's kind of a unique software and a technology. And I'm all for the novel things. The pervasive softwares, they're great to learn because you're probably going to be able to jump into them easier. There's a smaller barrier of entry, but novel things are cooler. I mean, that's just how it is. And just, we're not going to really be talking about 3D printing a whole lot. Maybe how it relates to DFAM, or design for additive manufacturing, which topology optimization and generative design are part of. But in our printer, in the 6K here, we have some parts printing. They are a topology optimized part, the one that we're going to be showing you. I'm actually printing these parts for a demo, so I can show them to students and people who are curious. But moving on, I use this remote control as an example here. We want to make this remote control as light as possible out of aluminum, say a 6000 series aluminum. But we want it to have a certain structural compliance, and it's going to take, say it takes a thermal load, or it's going to take a compression, some type of force. So topology optimization, kind of what I touched on earlier, is it's going to account for the boundaries, our buttons. It's going to retain those, and working around those, it's going to remove material in such a way that it reaches a target volume fraction. It could be 20 or 30% of the original volume while retaining that structural compliance. That can be, a safety factor, or, a certain mechanical property. all the softwares work a little different. SolidWorks is slightly different than Fusion. A lot of them are very different than Topology. When we're making our remote control, or what we have to show for demonstration, is it's a kind of a linkage or some type of bracket. And what you're going to see is, we start out. The cool thing with topology optimization is we don't have to model this remote control as it is. We can actually, it's more beneficial to not do that. I could essentially model a rectangular shape that's roughly the size of that remote control. I would have to lay out the buttons, have those modeled, or surface features modeled, so I can, define my boundaries. But I can do very little modeling or CAD work, and then I import it into the software. And what that's going to do, is kind of speed things up, and it will actually give us a better result. When we have a bunch of material removed away already, we've kind of preliminary done a lightweighting or a mass reduction function. So it's going to calculate with what's there. So if we leave it as a whole part, like a rectangular block, it's going to give it more kind of a better arena, or a better, vector, so to speak, to work from. And now, topology is very unique in that it's not a parametric modeling system or a direct modeling system, but an implicit modeling system. And what implicit modeling is, essentially, trying to dumb it down for everyone, and I'm not an expert on this. I'm getting more proficient with the software, but to speak on it technically, essentially, we have a workspace as you would with any software, and we have an origin. And from that, implicit modeling creates mathematical equations. So when you create things in like topology, such as a lattice structure or a very complex geometric surface, if that was what is considered a NURBS surface, NURBS, that's an acronym. Don't ask me to tell you what it stands for without Googling it. I've heard it a few times. But a NURBS surface is essentially what you would find on SolidWorks or Fusion or Creo, one of those softwares. It's how it, determines, the shape. And if we tried to run that, say we had a lattice structure, that's even an inch by inch with, 500 lattice cells in it, we would crash most computers. They just don't have the processing power. So, but what are computers good at is math. So it creates a field, kind of a graduated or scaled field. And from math, a computer works real well. It will actually essentially recognize certain points, and it can create a visual representation from that. So it's a mathematical field that is projected throughout our workspace from a center point. So it's symmetrical, or, it's plus or minus X, Y, Z. That way it allows the computer to compute. So we're going to open up the software here in a few minutes, and you're going to get to see. And now what you would do, kind of your workflow through this, is you would create a CAD part in a traditional modeling software that could, whatever you use. And then we're going to import it in. So when we import it in, then we're going to set up what are called blocks and workflows. And that's where we basically define our CAD and our features. Then we have to create a mesh. So any of you who are familiar with 3D printing or FEA, finite element analysis, we have a mesh. And it basically creates triangular shapes plotted around a surface that are, it's like as a form of tessellation in a way. When you tessellate a model, so when we apply mesh, it's just like when we make an STL or a 3MF file. It's a way for it to recognize the surface and be able to plot it out into layers and whatnot. So we're going to apply a mesh, and then you will basically have to apply that through the volume of the part. And then we'll define a material. So we'll give it a solid attribute. We can say it's aluminum 6061 or a 7075. It could be titanium. It could be whatever. And then from there, we have to make boundaries. If like a remote control has buttons. If it's a linkage or some type of bracket, we have to define, where the bolts or the hardware is going to mount and the actual surfaces of it. And then we set up our conditions, our responses, our restraints. We have to give it forces. We have to tell it where, on which surface or which direction. And in direction, we're going to call this a vector. Because it's not really X, Y, or Z, so to speak. It can be multiple, but where the force is going to come from, and we can have multiple forces. And then also tell it where the fixed faces are. So if it's a linkage, imagine an A-arm, on a vehicle or even a four-wheeler. You're going to have a point of contact at the top, and then the linkage is going to go down to something. So we're going to have a fixed face, where that's going to be restrained, and then our force acts on it. And then from there, we will simply run our topology optimization. We'll plug in all of our factors, and it's going to go through a certain amount of iterations until it finds the best iteration. And we can control and adjust it. And once we have our top op result, you're going to find that the surfaces are kind of rough because, that volume mesh through there is triangulated, and the computer, the software, it's going to try to pick the best lines and surfaces for strength. And then we'll go in afterwards. It has a smoothing tool, and it'll clean it up, and then we can bring in our features. So say we have a linkage and there's bolts, there's like bosses or like mounting points the bolts go through. We'll have surfaces defined, and then we will thicken those surfaces to the right, to the right diameter. And then we can join them all together. And anyone who's used any kind of CAD software, you should be familiar with the term Boolean. It's kind of like a combine, or you're taking multiple features and either using them as tool bodies or cutting bodies. And so we're going to use Boolean features to rejoin the CAD, the models, and then we're going to, finish up. It'll basically blend everything, and then we'll generate a finished part. So I don't want us to be stuck on a screen of a CAD software for too long, so we'll kind of run through it, and then, we'll discuss it a little more and get into like DFAM. So what you're going to see, so we have here as this is Topology software. And it's going to have a layout a little different than what you're used to with SolidWorks or Fusion. We do have basic, kind of tools here for modeling, creating certain objects. Here we have other operations. This isn't a really strong, CAD tool, so to speak, or modeling tool. There's very good uses for this. But what this is going to do, we have a lattice, section. And we're not going to make this video about learning topology. We can have another video or some YouTube series on that. But just kind of breezing through what it does. So we can create lattices. So with additive manufacturing, we have the ability to print hollow structures, and we can reinforce them with lattices. So we can have a very lightweight but strong part. And we have a lot of lattice methods and lightweighting methods, and so getting into the power of this software is that it uses fields and math. So in our blocks, we can actually create mathematical equations and variables that we can plug in to give us certain outcomes with our, our functions. Here we have for simulation. So this is our FEA. And we have utilities basically exporting and converting and moving stuff around. Now here manufacturing, because this is, goes hand in hand with additive, we have our slicing. So we can do a lot of different things with slicing, and it has an interchange here, exchange for certain machines. Now like Renishaw and EOS, those are two big companies that, do powder bed fusion, selective laser melting. And additive is really the power here. It's a power move with this program, what you can do. And we also see additive manufacturing here. So, hollowing, lattices, a lot of different stuff here. We have the EOS machines to build volume so you can work inside that space. Here's our material, more latticing and texturing. So we can actually add certain things to our surface. You can actually make really thin parts, but put ribbing on them, and the ribbing can be optimized by the FEA to provide the most strength. So it's a really flexible software. We have more of our our design stuff, our lightweighting, and then the power here is the top op. So essentially, what you see, I have this model. It's just a block, and it has 3 holes. So potentially, there could be a bolt. It could be mounting holes. All right. So what you're going to see over here, kind of how this works, is these are blocks. This is a workflow, a CAD workflow, and we have our blocks here. So you can see it kind of goes right in. And what's cool, we can label everything. You also have, we can look at information and properties and comments. We can do all that here. I'm going to import the part. And the search box, everything can be typed in. So, import, we can type in CAD. And we have all the things that related to CAD. So it's like you don't have to scroll up here and search for it. You can just type it in. And so we're going to import our part. And if I'll try to do this here where you guys can see it. So when I start selecting this stuff, now you can see, I'm defining my interfaces. So these are, it's going to interface with something like a bolt or dowel pin or whatever. So interfaces, then I can also say restrained faces. So interfaces would be all 3. Now these are my restrained. So say these are going to be bolted down, and then something's going to be in the middle might be applying a load. And there's my loaded face. Now I have to convert all the CAD to an implicit body. So that's basically, if I toggle this off, now you can see it changed a little bit. It's no longer recognizing edges. And when I have a CAD body here, you'll see I can actually pick surfaces or the whole thing. When I have the implicit body, I can only pick the whole thing. So it's basically what you're seeing. I know it's going to be hard to understand, but it's a mathematical equation represented, by a visual. The next workflow you're going to move through. So this is already, kind of been broken down. It's the FEA mesh. Now, generally how we would do this is we would remove this. We would say surface mesh. Or we would say like mesh from CAD body or implicit body. So we could say CAD body. Now, so I'm going to select my CAD body. Pick that here. So my whole CAD body, it's all a mesh now. And now what's cool about these blocks is I can make them a variable. So the way they are, if they're not a variable, I can drop and drag that into another So let's if I delete that, it's gonna like want to regenerate everything I've done. So I'll just, but I can make it a variable. And now I can drop and drag it in and it stays the same. And I can come back here and change any value. And then anywhere that's been applied, it will change that value there. If it's not a variable, then when I drop and drag it into another block, I've kind of lose it. You know, it's in there, but it's no longer able to edit. I can't go and change it as easily. So because everything can become a variable. And then I would mesh the surface. Now you see how there's like kind of triangles, you know, but they're not all the same. So I want to kind of like have those evened out. So I would remesh surface. And you're going to see, because it's a variable, I can drop and drag. I'm just going to give it some edge length. Triangle. You can see it's computing down here. Now look what it did. Now it made basically isosceles triangles. They're all equilateral or equal shaped. That's on the surface. So now I'm going to get a good read on this. But now I want it to go through the entire part, so I can make a volume mesh. I'm going to make this a variable. Remesh. I can just drop and drag. I can say 2 millimeter again. It's going to generate volume mesh. Sometimes it takes a little while. Let's go VM. So now if I did happen to do like a cut section of this, and don't ask me how to do it. I haven't really I'm not really sure how to get the section view, but essentially, if I did a section view here, you would see that inside of this that there's a, you know, that it's actually, you know, got these triangles all the way through it. I wish I knew how to show you guys. Anyway, we'll move on. I don't use the software to that level, but I know it can be done. So then from volume mesh, I would make my FE volume mesh, which is essentially what I have down here, FE CAD solid mesh. Do it a linear. All right, so it's done. We're going to delete these so they don't. You can see how that kind of works. So I have my FE, my finite element mesh. So I have a mesh across the part and through the volume. The next step would be to, you would see, is our boundary and conditions. So I'm going to set up a material. Now, this is a material, I was kind of playing around with some stuff. This is kind of like a polymer material. You can pick. There's tons of materials, and we kind of saw that. So you have here sample materials: stainless, titanium, tool steels, you know, and then some aluminums. If you know your properties, you can set up your own material. And then so restraint loads. So if you see when I click on that, so these are restrained faces. It's going to create nodes or cells, you know, through those holes. And it's going to pick CAD faces. So that is why I set up those CAD faces the way I did. And then our force loads. So it's going to be in our loaded face. So there in the center. So then our applied force. This is just saying this is our face boundary. So these are our boundaries where the force is going to be. And then we pick a force. So we're telling it force loads, which is our boundary. Now you can see here, these little arrows will tell us the direction. So I have 1,000 newtons in the Y and the Z axis. So 1,000, so it's going to 1,000 this way and down. So it's a vector of, essentially a 45-degree angle. So if we had something bolted here, and now if we had a whole assembly with all the linkages, we could actually make tie constraints. But essentially this is going to represent, there's a part bolted here, but if it's an A-arm, and this is a bracket that an A-arm, the angle is going to come down and press on it. So the force, and now we have our displacement restraints. As you can see here, those are restrained faces. Now, here's where we come into some of our responses. So structural compliance response. Through our fixed restraints and applied force, that sets up our structural compliance. And then our optimization constraint. Now this can be done a few different ways. This is a volume fraction constraint. So 0.3. If we did, say we did this, let's do divide. All right, so here's where the cool thing about the math is. So I can say, let's say we want 30%. I can say 30 over 100. That's 30%. Now this, I can even make operand A a variable, so I can change that anytime right here. Now you can see it's going to regenerate the top op because I just did all this. I could actually back up, and it's probably going to want to regenerate it anyway, so we'll just let this go here, and we'll discuss something for a minute while it's... That it will be kind of regenerating. There's a lot of... Well, keep it in the background, let it work. So one thing with the software, it is going to use a lot of computing power. I mean, computers are good at math, but it will take time. You can see kind of how I had that set up. How it kind of goes right through. And I'm basically telling it, here's my part. Here are the features that I want to keep or that are important. Here's what those features are. They're either restraint or loaded face or fixed position. Here's the amount of force I'm putting on it. And, then it's going to generate, what I want to get out of it. I want to reduce my my volumes. I want to do whatever. Let's check in and see. Okay, so it's done generating. You can see the power of the math here. I can set that up. 30 divided by 100, it's going to be 30%. 30 out of 100. So the math, it's kind of really cool, and this is very simple. But you can do that with anything. I can do that with densities of lattices and all that stuff. So then we're going to come into here to our top op. When I click on this, you're going to see something very different. So this is our top op, our single body topology optimization. So this is just one part. We're just having a theoretical force from another part without having that modeled. So we're going to have, and it's click and fill. So if we click, I don't want to remove that because then when I'll add it, it's going to try to run it again. But essentially, I have the FE mesh set up, and when I double click in this box, the design space, it's going to ask me, anything I have that is made a variable in a block, it's going to be right there. So I can just double click, select, and go. Or I can drop and drag into these fields. Our material is defined. Our responses, our constraints, our responses, our max iterations. All right. So now I have this. Something's highlighted here. So I want to, there we go. That was our mesh. All right. So if you see that says hid, so that's going away. This is our top op. This is our result. So you can see in the center here, it left kind of an area where that loaded faces, and then we have, you know, two kind of circular parts here. So it removed enough material, you know, so it kept our compliance. And now here, if you see, I can slide this and it's going to change. It's basically going to take me through a threshold. So 0 would be a complete part. 1 would be basically nothing. We can keep adding material. Now, 0.5 is the middle of the road. And I can see it went through 26 iterations. So if I start sliding here, you can see the different iterations it went through. And then from there, I can remove material. So if we go our full iteration, that's the best result it came up with. So now, say we're happy with this. This is good, but we can print that. If you look, these are all the little faceted triangular faces. So we don't want to print that. It's kind of rough. So it has tools built right in. This is our optimized body. So let me shut this off. See that? We have this, it'll kind of like do it quickly for us. It'll perform all the smoothing and everything. That's kind of the cheating way to do it. We can actually do a smooth in body. And we'll click here. I'm not sure which one is what. So we can just drop. Okay, we're going to have to make that into an implicit body. So implicit body from topology optimization. We're going to grab this top op, drop it in there. All right. Top op. Now, I'm going to drop that in there. And it's going to give us, make sure these aren't highlighted. And that's what it gave us. Now, how close is it to this? It's very close. See, there's like a little bit of rippling. What we would do is we would come here and we would play with our grid size and our smoothing iterations. See, although these are close, see this one's set to linear and this one's on cubic. So you can see normally we could just do a smooth the body like this and we can play around with it. We'll just delete that. So this is our top op result that's been smoothed. Now part features. So I need to add back in my bosses now. So with a Boolean union, you can think of union as kind of a connection. We're going to basically add these bosses back in. You can see when I click, look, it generates, all right? So now it's imported these CAD bodies, these faces. So I have the faces. It then makes those implicit bodies from the faces. And then it will thicken them to 3 millimeters. And I can change this at any time. I can change that to 2 millimeters. And anything after that is going to re-output those. All right, so now they're 2 millimeters thick. I can put a blend radius if I want. That can be done later. All right, so we move on. So we have those. We basically brought those together. Now, so we have, and we're going to make that a variable. We're going to call that part features or interfaces or mounting points, whatever you want. And then we're going to do another Boolean union with our top op plus our part features. And this, you see, it's gonna load just a little bit. We're gonna remove that. Now you can see it actually joined them and it blended it. See, I have a blend radius. I can put 2 millimeters in here, and it just blended even more. So whatever you want, you can kind of do that, make it look nice. But now, these are kind of puffy. You know how they expanded not only diameter but actually. So now I need to do a intersect. I need to take, my original features and my smoothed top op part and kind of subtract. So you're going to see my implicit body from CAD body. So my imported part. It's going to take my original geometry. And then this, what we're seeing here, this top op plus interfaces, smooth, it's going to take those. And it's going to give us a result. So see, wherever they intersect, so that my original surface, is nice and flat. And that's what it gave me there. Now that part's done. So I have my original faces, say that's going to mount onto a plate, or there's bolts, you need a nice flat surface. If I have a bolt, so here's my original body and, the thickened bosses. Now I can't have that. Bolt's not going to sit nice on that. So we do the intersect, and that's what it leaves me with. Then I can just translate. Now you can see I actually have moved. I kind of set this up for us. So we can see, so this is my original part. Let's see, this is should be our top op. Yes. So now if I have that translated, so if I shut this off, I can actually go back and set my top op. You can kind of see the phases or the stages. I started with a block. I got the top op result. Then I smoothed it and re-added my boss features. So that could be, some kind of bracket. That's just an example. It's not a real part, but it can apply. That's basically the method. And down here we can see we just export our mesh, and that's where we got that. So I didn't want to have the CAD screen up there the whole time. So what do we take away from this? It's a tool to design something based off some engineering factors. Top op is kind of straightforward. Generative design, if we were making that same part, we would tell it, we're going to make it out of, make it on a filament machine. So it may try to give us, orientations on how to print it. It may know, based on that process, that it needs material in other areas. And it's going to give us multiple options. It's going to give us all the iterations instead of taking a blend of one, essentially. We'll be touching on generative design. It's a very powerful tool as well, and it has very unique applications. I think when you get into, and the one thing with generative design, say I have a motorcycle and I want to build a swing arm. A swing arm is what connects from the frame to the rear wheel and the suspension. So I can have the motorcycle, modeled. I can have the rear tire, the engine, all the sprockets, the chain, all of that. And I can say I want to avoid all of these features, and here's my design parameters, and it might give me 10 options on how to do that. And then in those 10 options, I can filter it down for additive process or a CNC machining process. So generative design is a little more in-depth for the manufacturing side, where top op is a little more leveraged towards, engineering. And, engineering can be more than just, structural. It can be thermal. It can be, electrical. It's electrical, magnetic properties. Thermal, obviously, whether it's convection or, induction, radiation, the kind of thermal forces or loads it's going to experience. It can be harmonics. That's pretty high level stuff for, most of what we're going to discuss. Maybe in some future podcasts, I have some people I would love to interview. So kind of, I hope you're able to get kind of the gist of what Top Op is. I mean, we went through it. You can kind of see the process, and every Top Op software is going to be different. They're going to require the same, basic functions or basic requirements, as far as constraints, and responses and boundaries and whatnot. I may do a video. We may have like a little follow up with SolidWorks, a topology study. It's not going to come out nearly as great as what you're going to see here. And SolidWorks doesn't really have a way to smooth out the part. You're going to have to take it into a CAD, an OBJ file or STL, like a mesh mixer or something, and try to smooth it out. There's some other softwares. But the one thing I want to touch on is, design for additive manufacturing. So when you approach, a design with AM in mind, you're going to use AM process. It kind of it creates degrees of freedom that we don't have with conventional processes like machining. Because I can print essentially any shape, it can be amorphous, any organic, compound geometries and surfaces. I have the freedom, so I can use softwares like, topology optimization. And, just thinking back about it when I first started learning CAD and learning about design, this wasn't around. And there were a couple softwares that were starting to touch on it. And, it just wasn't a big thing. And I kind of always keep an eye out on what the next thing coming is. And I can tell you, because of the flexibility and adaptability of like topology, being it's a math field driven system, I don't even think their applications engineers know its full capability. If you're trying to accomplish something and you don't know how to do it, you can call their applications engineers and they will literally get on a Zoom call or go over your parts for you and come up with figure out a way. Or they have a lot of beta features. I don't think that I have them loaded here. It's a preference. And I have to change the preference. They have some beta features that are specific to additive manufacturing, like overhangs. It will add or prevent overhangs or a certain degree of angle. That is one, overhangs. When you get into additive, then you have to start supporting things. And when we add supports, then we have to remove supports, and that can violate the surface, or it can cost more. It's an extra material we're putting in. So like when we have filament, FDM or FFF, if you need support material, that's a whole different roll of a spool of material, and it has to stop printing. Each layer, it'll stop printing the primary material, and it will purge and come back in, if it has a singular extruder, and then it will build the support material, and then, there's a purge tower, or, there's a few different words for it. Essentially, it slows down, your print time. Now with like resin printing and metal, sintering, it's going to print the supports, as it goes. There's a lot less changeover, so it is quicker. But in resin printing, supports, they actually touch the model. They violate the surface. We have to, sand those off, or else they leave divots. And in metal printing, if they don't bust off, then we have to machine them off, or grind them off, and then still treat the surface. So, when you're doing design for additive manufacturing, these are the types of things that you keep in mind. I can use softwares, like Topology or Fusion, for generative design, and it really opens up your options. You're no longer limited, and you can also start thinking about more factors involved. Maybe you go into it thinking, oh, I'm gonna have to make this out of additive, and then you find out, well, there's an option. The software is giving me an option to use CNC machining. Or you think that you're gonna have to machine this part, and then you come to find out there's a better, lighter design that can be done with additive. You I don't know if you've seen there's some of these parts, they're kind of like spindly, and you'll see like a corner bracket, for a bookshelf, and it'll have all these like spindly organic arms. Now that's exactly generative design and topology optimization. You're not going to machine those. Theoretically, on like a 5-axis milling machine, you could put those right on there, and the machine's going to move all over and articulate and come in, and it's going to machine that, but it's going to take forever. Where I print it, I throw it in my powder bed machine, it's just going to go boop, 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 and it's going to like print them right away. So, these the degrees of freedom really open up. And then, we also think, there's the intricacies of, additive manufacturing. So like overhangs they're kind of a issue. There's systems out now like melt pool monitoring and flow control and variable parameters that like company like Velo 3D they're coming out with, so you can print support free. And the resin game, that's tried to big, like everyone's trying to print support free. So the parts can really be optimized to avoid that kind of thing and just make it a little more streamlined. They can also be, especially with a process, any additive process, since you're adding material, when you can reduce the mass, you're reducing the amount of material that's involved. It doesn't always necessarily mean you're reducing the time, but we're reducing the material needed, so that kind of lowers our input cost. Then we can maximize, our profitability. But I think, that's about all I want to discuss now. We're going to talk about generative design. I just kind of wanted to overview topology optimization. This wasn't going to be like a teach you how to use the software kind of class, just to understand that it exists, kind of what it is, and what to look for. Now, one thing I do want to show you guys, or at least discuss, if you've been on our Instagram page, you'll see there's a video where we did a time lapse with a resin machine. Now, this is kind of just like a little extra, something kind of cool I want to mention, so you guys can go check it out. We're going to do a couple more of them. So I don't know if any of you have seen these time lapses with 3D printers, like filament machines. Essentially, you have like the printer, and then the part will, it looks like the part's growing up off the table. And the printer, the extruded head is never there. It's just like the part. So I've kind of done the same thing with a resin machine. And how you accomplish that on a filament machine is you have to use a microcontroller like a Raspberry Pi or an Arduino board. And there's a program called Octoprint. And essentially it will, it kind of interfaces in your G code for the filament printer. After each layer, your gantry, your extruder head will go to a position with a G00, which is a rapid move, or G01, linear move. And once it gets there, the G code will then trigger, and I'm not exactly sure what code it is, but it will trigger, through your controller, it'll trigger the camera for the shutter release. This does layer by layer, and then you basically put together, you stitch those together and create a video. So now I've done, with the UV system, in the resin machine, there's no the G code, there's no G code that's kind of similar to filament. The files are kind of closed looped. Technically there are G codes, there's you have to have a link between the machine and the camera. So, how does it send that G code? And you're not gonna, crack hack these resin printers with a Arduino board or anything. They don't have a port for it, and you'd have to kind of build your own interface to connect them with. So what you can do is take advantage of how the cameras are designed. So, like, what I have is a DSLR camera, and they have an accessory port for a remote, like a remote shutter release. So they actually have like cords with a button on it, and I can hit it, and it'll go and it'll take the photo. All that does is it takes a low voltage, and it's just a series circuit. So here and back, and that's just connecting. It's open or closed. It's open. When I hit the button, I close the circuit. I make it a closed loop, and it'll active. Trigger the camera to shutter release. So, you know, what was figured out is, how do I do that, but with the UV light? So every time this printer, it does a layer, the UV light comes on. So how do I, use that to shutter release? Well, it's very simple. Just like the thing that's used in night lights or street lamps, that's a photoresistor or a photovoltaic resistor or a photocell. And a photocell, it looks just like a little resistor, has two wires, and then you have the cell button on top. And basically, when light hits it, uh, the electrons excite and they jump and they create a circuit. So when the UV light comes on, basically it's the photocell is soldered into a cable that has the right plug on the end, and you just feed it into the cabinet of the machine. Like mine, I can feed it in through the back, and I get it up kind of close, within half inch of one of the UV the LEDs down there. And then when that comes on, it picks up that light and it will send the signal, and it'll take a photo. So like I had 1,300 layers. It took 1,300 photos. Now the only issue is when a resin machine is done, the last layer, then mine will wrap it up out of the table to a certain height. So you're not going to catch that. Your video is going to end. So then what you do is you just manually jog the part back down into the resin, into the vat, and you can set the camera on like a continuous capture mode. Technically, you could make a little video, have it record, and then come up out, and you have to blend it in there. But you can just have it like where it'll take like 6, 8, 10, 15, whatever, shots. And I can like set my machine to move the Z 10 millimeters, and it'll come up and it'll take all those photos. So I kind of make like a little section at the end just so it'll come up and clear out of the resin. But I did that. I made a time lapse. I'm going to do a couple more and try to make them a little better. So just wanted to give that shout out. So this is actually, the rig. So I have the cable. It has the accessory port on it. And that's a photo cell. You probably can't see it. So what I've done, I've actually recreated the process here, or the theory, with an Arduino board and a breadboard. So I have a little video that I can show you guys. Let me pull it up here. If I can get it to work. All right. See, when I cover up the photocell, the LED goes out. When I release it, the light hits it, the LED turns back on. So that's basically the theory. I just set that up. I have a little Uno R3 Arduino board here, and with the IDE, I just write a simple little program where it'll take from the 5 volts on the board, pump it in through the photoresistor, and then I just covered it up with my hands, take the light away. The LED went out. It's how it works. Now, if any of you are ever kind of inquisitive, I think our next maybe our next podcast will be on this. We'll talk about circuits. I know it's kind of a little out of the realm of like what you think manufacturing is, but it's electronics manufacturing. We'll do like a basic circuitry thing, and we'll actually there's some great resources like Tinkercad. You can create interactive functional circuits, even code for them. With like C++ and Arduino and whatnot, you can build fully functional circuits. It's like virtually, it's all interactive, very intuitive too. It's a great way if you don't have like, actual like electronic stuff here. I have a whole bunch of things, breadboards and jumpers and all kinds of, stuff. So sensors and, LED segment displays and all, rheostats and potentiometers and all that. But maybe we'll do a little electronics thing. We'll kind of just give you an introduction to, especially for those young kids out there who haven't touched it. This is becoming a very big thing, like PLCs, coding, microcontrollers, because you're learning how to build systems. You know, uh, even like these 3D printers, they have a motherboard in them. You take like a filament printer. A lot of them, people are controlling them with Raspberry Pis, with Arduinos. They have very simple circuitry, and you can actually make mods yourself for them. So yeah, maybe that's kind of good. We kind of inspired ourselves, but I hope you guys have taken away some good things from this. We're over an hour. It's the longest podcast we've done. I really thank you guys for all your support. We've been getting emails and we've been getting messages on our social media, like Instagram. There's a lot of people that are just, I'm very new at this, as I say every time. This podcast thing is like, it's not really my thing. I'm just trying it. I'm having fun. Um, we're trying to like provide some good information to everybody, and especially the young guys and girls out there, in high school, entering the college or in college, and you're just really, hungry and trying to like pick up any knowledge you can. And we're trying to bring it, as real life. We're not speaking, fake here. you know, I love watching Pat McAfee show that kind of like covers sports. And he always his intro. We don't have that fake ass celebrity, network that I don't want to be, polished and, all, scripted and rehearsed here. We're just talking from experiences, people who have, you know, been in industry, who've been in manufacturing, who are engineers, who are makers, just telling how it really is. So we don't want you to be surprised. You're going to be surprised enough. We don't want you to like have some faux, outlook or on what things are going to be. Um, you know, I really just want to do this to kind of share my knowledge. I like teaching, and I like teaching young people. So I decided, hey, let's just make a podcast. Let's mess around. Let's talk about some stuff. Try to put out, we're not going to put out false information. We're going to put out real life information from experiences. And we've just been getting some real positive feedback. Now, we don't have a lot of followers on our social media, but we keep grinding every day. We're not out there trying to score big on, YouTube money, because we're not going to get it. But we're just trying to have fun. So I encourage you guys, check out our Instagram. We really like Instagram. We can share our stories and our posts, and our Facebook. We have a LinkedIn page for anyone who's there. Obviously YouTube. So we're recording this now, and I'm still learning how to do these editing things. With the video and the sound, and how to bring in my overlays, and I kind of just wing it. I do put in time to learn, but you're not going to learn unless you try it. So, that's what I'm doing. And if it's low quality, I'm getting out of it what I put into it, but, I'm going to learn. You never come out hitting home runs to begin with. So I just thank you guys. Just check us out, our Instagram, YouTube, Facebook, LinkedIn. We have our website, themanufacturerspodcast.com. All all of our podcasts are there in the audio version. We haven't. We might start putting our video on there, but we'd rather just have you guys head over to YouTube. We do have a Patreon set up. We love support of the show. We can do more things, and really become more involved with everybody. And we're just gonna keep grinding. We're gonna keep doing it. We're gonna keep making videos, putting stuff out. I feel bad. I've been telling everyone we're gonna have guests on for a while, and it just hasn't panned out yet. With kind of everything starting to return to normal after the pandemic, schools are kind of unrestricted now. So colleges, and a lot of my good friends are teachers, in STEM. So they just been really busy, and they're trying to make up for lost ground, and virtual learning is not as good as in person. So we will get somebody on here soon, I promise. I've got a handful of people. If anyone listening, any of our viewers or listeners, if you would like to be on the podcast, shoot us a message. We'll discuss it over. If there's some good content, we can share some good stories. I'm all about it. Just thank you guys. God bless America. I'm not going to say go Hawks. I'm a Seahawks fan. My team just traded away their greatest quarterback ever. So now I'm going to go. Now I thought about it again. I'm probably going to go cry. But thank you guys. And let's keep on keeping on.